All right, without further ado, I'd like to introduce tonight's guest speaker, Dr. Anita Cochran. So Dr. Cochran is an astronomer, planetary scientist, and senior research scientist at the University of Texas at Austin. She's also the assistant director for research support at the McDonald Observatory. She was just telling me she was at the McDonald Observatory last week, correct, Dr. Cochran?
That is correct.
Yeah. She focuses on the study of primitive bodies in the solar system and the composition of comets. She earned her bachelor's degree from physics from Cornell University and then went to the University of Texas at Austin, where she completed a master's degree and PhD in astronomy. In her astronomy career, Dr. Cochran has taken on numerous high-level leadership roles. She served as the chair of the Division for Planetary Sciences of the American Astronomical Society from 1995 to 1996, and a committee member from 1989 to 1992. She's also served on several committees for the National Research Council, including the Committee on Planetary and Lunar Exploration, COMPLEX. She was a co-investigator on the Comet Nucleus Tour, or CONTOUR mission, and on the imaging team for NASA's Comet Rendezvous Asteroid Flyby mission. She's currently a member of the International Astronomical Union and the National Optical Astronomy Observatories Council. We're delighted to have Dr. Cochran here with us tonight to talk to us more about the formation of scenario for planets and what comets represent in that scenario. Without further ado, Dr. Cochran, I'd like to pass the Zoom over to you.
Okay, thank you. Let me share my screen. That one. I just have to figure out which window it's trying to share. Okay, so as some people noticed when I put this up as a test earlier, there's a picture on the screen that is connected to Houston because it was taken by Ed Shapansky. That's McDonald Observatory's 82-inch and 107-inch telescopes and Hale-Bopp. It is really a Photoshop picture because it was put together in the photo lab, not done on the computer. I've always thought that was pretty cool. But it's also one of my favorite pictures of comets because it has a great comet and our telescopes. So stars are born deep inside very cold, dark, optically thick clouds. So on the screen, you have two pictures. The left one is a picture in the optical. And so you see this big black, let me see if I can get by, there we go. Big black thing that's doesn't have any stars in it because it's a really dark cloud. And then in an infrared telescope, this was the Spitzer Space Telescope, a little behind the current JWST, you have this infrared picture of the star that is forming in that. So it's the same exact field, but you get very different pictures based on what wavelengths you're looking at. So if we look at an area of the Milky Way that has lots of stars, lots of nebulosity, it also has clouds. We're going to zoom in and look at one particular region, M16, the Eagle Nebula. This is, of course, the Hubble Space Telescope picture, not, again, James W., but I have the sequence from Hubble. I don't have it from James W. JW. So if you look into the Eagle Nebula, and you can see at different wavelengths, you'll see here, there's a box, and it's outlining one of the fingers that you get in the Eagle Nebula. It's a pretty spectacular nebula. And if you zoom in on that finger, you'll see there's actually three fingers, and there's some stars, and then this whole thing. And we're going to continue to zoom in, and there's a little finger at the end of the finger. And when we zoom in once more, that is the size of our solar system. So the universe is rather larger than we're used to, especially in our solar system. But that dark cloud is where systems like our sun will form. Now, we have a whole history of making models of the formation of the solar system. Unfortunately, we've always done it as isolated stars. And if I go back 1 second, you can probably guess that there's probably other regions where the stars are forming in that whole region. But this is the way our theories go. We start with a dark cloud. We have cores, little increases of material, which then have more gravitational pull than anything around them. And so they start pulling on things. And pretty soon it collapses into a more compact region. It's falling downward. The unit that's on this screen on the bottom here is 10,000 AU, and AU is the average distance of the Earth to the sun. So this whole bar here is 10,000 times the distance of the Earth to the sun. And you see it starting to collapse at approximately t equals 0. And where we define t equals 0 is a little complicated, but It continues to collapse, but as pressure is increased, the protostar finally gets to about 1,000,000 degrees and starts to actually become a star. And so it has material that's flowing outward through the poles because the disk here is blocking it. So there's still material falling down here and material going outward. This is 10 to the fourth, so 10,000 to 100,000 years from the formation of the star in the first place. And the outflowing material starts to dominate and clear out the material around it. Then you end up with a disk, which has regions where the planets are going to form. So this is a pre-main sequence star, which means it's not quite an adult yet. This is the remnant disk, which occurs at about 1,000,000 to 10 million years. It's actually probably closer to 5 million years when you get something like Jupiter forming. And then, of course, you have the solar system. In this case, our solar system this is Pluto coming up here, and then all the rest of the planets in there. So that's our picture of star formation in isolation. Oh, wait, there's not 9 planets. That's a bad slide. Let's try the 8 planets. So this is a composite image. It does have Pluto on it, but we now consider that Pluto is not a planet. It's a minor planet. And that's because there's lots of other objects out in that part of the solar system that are about the same size. But this is a composite image from NASA pictures of the major planets. And Pluto is this little guy here, and this is Renu. It's an asteroid. The planets are not to scale on this picture, obviously, because Jupiter here is about 300 times the size of the Earth. But the important thing is the planets all orbit the sun going in the same direction. So, they're going around in that direction, all of them. And they're in the same plane as the Earth's orbit. So if you put the sun and the Earth on a table, Jupiter and Saturn and all those planets would be able to be going around the sun on the table, so the same plane. And we call that plane the plane of the ecliptic. Now, it's a slight exaggeration because there's a little bit of tilt, but it's not very much. Jupiter is tilted 1.4 degrees from the plane of the ecliptic. And most of the planetary orbits are essentially circular, Pluto being an exception. Pluto's always an exception because it's more of an ellipse. So, like the planets, comets orbit the sun. But unlike the planets, they don't necessarily orbit in the plane of the ecliptic. So they actually have no preferred orientation. Comet Halley travels backwards to the Earth's direction. It's in almost the same plane as the Earth goes around the sun, but it's going the wrong direction. Hale-Bopp was about 90 degrees to the plane of the ecliptic. We just had Comet 2022 E3 ZTF, which some of you may have seen. That one was about 107 degrees, so almost perpendicular to the plane of the ecliptic. And most of the orbits are highly elliptical. Now, some of you, I'm sure, haven't been in school in a while, and you might not remember exactly what I mean when I say elliptical. So a circle is got no ellipticity, and as you go to higher eccentricity, they become more and more elongated. So this is more like the orbit of Pluto, so very, very elongated. And that's called the eccentricity of the orbit. And in something like this, the sun wouldn't be here. It would be here at one end or the other. And the planet like Pluto would come in and be coming from very far away and then get really close to the sun and shoot out again. And it's fastest going around near the sun than it is out further. So as the comet approaches the sun, it's heated. And in the low pressure space, the ice, which makes up most of the comet, is converted to does not get converted to liquid like it would if you put an ice cube on the table and let it sit there. Instead, it's transformed directly to the gas stage. And that's because there's very little pressure and it's reasonably cold out there. So that process is known as sublimation for all the non-chemists in the room. And we talk about the ice is subliming. The teeny nucleus, and I'll talk about size in a minute, has very little gravity. And so the gas escapes outward from the nucleus when it's heated. It actually also has not only has very little gravity, it has very little strength. These things are pretty amazing. So the escaping gas carries with it some of the dirt. Now, what do I mean by dirt? Well, it's just what you think is dirt. It's stuff that like sits on the ground. It's all sorts of, pieces of rocky stuff. And comets have dirt in them. The escaping gas and dust form an envelope around the nucleus, and we call that the coma. And that obscures our view of the nucleus. So we don't ever image the nucleus from the Earth. We don't even image it very well from space telescope when we can on a very far out objects. But anything in the inner solar system, we don't actually get to image the nucleus. We can when we fly spacecraft close to them, but we've got to get inside that coma, because that coma obscures our view of the nucleus. The other important thing to know is we see these comets come in and they have this beautiful pictures of them, but that's coming from very little surface of the comet, because very little of the comet's surface is actually active. We see almost no ice on the surfaces when we fly by. And indeed, the surfaces, much as we talk about its ice and we think of ice as being white, the surfaces are almost totally black. So comets that we see today in the inner solar system come from one of two reservoirs. There's the Kuiper belt, which is the continuation of the disk of the solar system past Neptune and going outwards probably about 50 to 100 AU, so 50 to 100 times the distance of the Earth to the sun. And that Kuiper belt is mostly primordial. The other thing we have is the Oort cloud, which is a spherical halo of comets out to about 100,000 AU. But they weren't formed out there. They were actually formed in the region of the giant planets, Jupiter, Saturn, Uranus, and Neptune. And then gravitational activity of the major planets, Jupiter and Saturn especially, will pull and push them until their orbits change, and about 90% of them get thrown entirely out of the solar system. And the other 10% form this Oort cloud. So this big spherical halo of comets. If you're having troubles visualizing this is an image that tries to describe this, and you see this big Oort cloud, and there are comets in between, but this big Oort cloud, it's about 100,000 times the size of the distance from Earth to the sun, and then deep inside it gets more dense, and this is Pluto's orbit, and all the other planets' orbits are down deep inside there. So that's what our solar system looks like today. As I said, these objects actually formed in the Jupiter-Saturn area. And there's probably many billions of comets. One of the most amazing things about this is called the Oort cloud, after an astronomer by the name of Jan Oort, who was Dutch, and who basically studied everything in the universe from A to Z, literally. There are constants named for him from A to Z. But he had 19 orbits of comets that were out near the outer edge of the Oort cloud. And from that, he deduced there had to be an Oort cloud, which is an imagination I don't even possess. So we sometimes break comets into different types of categories. We talk about long period comets, which includes the non-periodic comets. So these non-periodic comets are ones that aren't going to come back, or at least not anything, in anybody's reasonable lifetime. And the long period comets, example is Hale-Bopp, 4,000-year period until Jupiter perturbed it, and then it became a 2,000-year period. Those comets all reside in the Oort cloud for most of their lives and only occasionally come inward. For things below 200 years, we arbitrarily call those short period comets. Now, short period when you're 200 years seems a little wrong, because the human lifespan is not anywhere near 200. But that's the groups we break it into. And those are then broken into two subgroups. The Halley-type comets, not surprisingly, Halley is a Halley-type comet. And those are periods from 20 to 200 years. And they came from the Oort cloud. And then there's the Jupiter family comets. The name might tell you that there's some influence of Jupiter in there. Those are periods of less than 20 years. They never get that far out that Jupiter's gravity isn't always affecting them to some extent. The shortest period comet of those is Comet Encke, which has a 3.3-year period. So it never actually even gets back out to Jupiter's distance. It only gets to about 4.5 AU. But most of those comets formed in the Kuiper belt. So we have samples that come into the inner solar system that are both Halley-type, Jupiter family, and long period comets, all three. So how do they get from the outer solar system to the inner solar system? Well, one possibility is giant molecular clouds. We talked about this planetary system forms in giant molecular clouds, and maybe giant molecular clouds in the galaxy perturbed them because our sun is going around the center of the galaxy, and they're at different speeds from other things. But we can figure out, because we know a fair amount about the area around us, and we figured out that a giant molecular cloud will only come by close enough to have any influence about every 300 million years. Not too often in a 4.5 billion year system. Well, maybe that's nearby passing stars or stars that are burrowing through the Oort cloud. Well, that will work, but over the life of the solar system, about 5,500 stars have passed within 100,000 AU of the sun, so within the Oort cloud. And maybe they've ejected about 10% of the Oort cloud population, but only 10%. And so if you had a star the mass of our sun passing through the cloud at a typical velocity, because they're on different orbits around the center of the galaxy, and the typical velocity is about 20 kilometers per second, it will eject all comets within about 450 AU. And so it'll take a cut through, but everything else doesn't even notice that anything's happened. So that's not going to work. So what is it? The galactic gravitational field. Our galaxy has a big black hole in the center, and everything goes around, and there's tides. We think of tides only in terms of water, but there are tides from things moving around in the galaxy. And that's the dominant force acting on the Oort cloud. So if this is correct, and we have lots of models that show it should be, the cloud should be sort of football shaped, prolate spheroid. It's long axis points towards the center of the galaxy because that's where the most pull is. And it's maximally 100,000 AU or 100,000 times the Earth's distance to the sun for things going around in the same direction as the sun, as the planets in the plane of the ecliptic, and about 120,000 AU for things going the wrong way. Because of the way the gravity works, they come out slightly different. Okay, so I've told you all about we form comets, where they form, how they get in the interstellar system. But why would we want to study them? Well, comets are the least altered objects left over from the formation of the solar system. And they built the planets in the outer part of the solar system. So they're icy bodies, and when they came together, they formed bigger and bigger objects. If you tried to study Jupiter to understand the early parts of the solar system, you'd have to contend with all the things, all the storms and everything's going on in Jupiter. If you try to look at the Earth, well, we've had a whole history of 4.5 billion years, and we have earthquakes and clouds and rain and snow and, oh yeah, life. That's another thing that can really have an influence. But comets are small. They spend most of their life in the deep freeze of the outer part of the solar system, and they don't come in very often. So they're very little changed, not changed, but very little changed from when they were first formed. So if we study them, we learn about conditions when they were formed, which is 4.5 billion years ago. Do they contain things that before the solar system were formed? Well, there are people on both sides, and one of them says that they're conglomerates of unprocessed interstellar grains. Another says that all the pre-solar molecules, all the pre-solar system molecules were completely destroyed, and the material is homogenized, and nothing's left from before the sun started. There's probably truth to both of them, probably a little bit more on the second one, but there's reason to believe that both of those have real possibilities. So comets are basically dirty snowballs, or as we've studied them more, they might be muddy ice balls. They're about 50% of the mass is ice and 50% is dirt by mass, not by volume, but by mass. And 80% of the ice is water ice. Now, when we say ice on Earth, we tend to think in terms of water ice. You know, you go to the refrigerator, or the freezer, get out ice and put water on it, and that's your ice water and stuff. That's 80% of the ice in the comets, but that's not the only thing that's there. There's other ices of methane, ammonia, carbon monoxide, carbon dioxide, ethane, formaldehyde, on and on and on and on, ever smaller amounts of things. And the nuclei are not very big. The nuclei of the comets we see in the inner solar system are typically a few kilometers across. So Halley is 6 by 8 by 8. Borrelii is 8 by 4 by 4. Hale-Bopp is huge. It's 25 kilometers. Now you're sitting there going, kilometers. I work in miles and all that. Well, you know, there's 0.6 miles to a kilometer. So they're not very big. As a matter of fact, we've flown past a bunch of them. with spacecraft. Here's pictures from them. Halley was the first one we flew past, and we didn't really understand much about comets. We said, ice has to be bright. So let's target the brightest thing as we fly past so that we can, image the surface. And the brightest thing, as you can see, is this thing here. It's a jet coming off, and this part is really pretty dark. And they actually pushed the image out of the field of view of the camera. Oh, well, we learned. This is Stardust 2. Stardust images of Vil 2 looks very, very round. It's about 5.5 kilometers across. This is Borrelli from Deep Space One, slightly larger. This is Temple 1 from Deep Impact. We actually took a little spacecraft up and put it in its way, and the comet ran into the little spacecraft, and we watched to see what was going to happen. It wasn't exactly what we thought was going to happen. We discovered that they're really, really almost like talc. They're so soft. But we also, when we got back the images and started looking at it, you can sort of see a line here. Does that mean there's two pieces together? And then there's this really smooth thing. And we all said, oh, that must be a low spot, and it's filled in with ice. When we got enough information to have topography on it, we discovered that's a high part. That's a mesa. Didn't know that could happen. And then this spacecraft went on to fly past this object. Oh, no, sorry. This spacecraft went on to fly past this object. Got it wrong. This one flew past this one again, but flew past Hartley too. We renamed the spacecraft Epoxy, and that's a little guy. And I'm going to talk more about him later at the end because he's got some very interesting things going on. But as you can see, he's sort of a peanut shape, and he's very active at one end and a little less active at the other end. This is the European Space Agency's mission to Comet 67P Churyumov-Gerasimenko. I just find this movie fascinating because it's this little rubber ducky who's rotating in space, and it's great fun to watch him. But we actually landed on him, which didn't go exactly as planned to start with. We landed and bounced and landed and bounced and landed and 4 times before we came to a rest, and then we were under a boulder. I shouldn't say we. I wasn't on that mission. Okay. Requisite pretty picture. This is Comet 2020 E3, F3, sorry, Neowise. The picture was taken by Jimmy Lowry he lives out near McDonald Observatory. This was taken in the parking lot of the Hobby Everly Telescope. I think it's a gorgeous picture because you shouldn't have clouds, but it still makes the comet look really good. The nucleus is buried way down in there. You can't see it. And I talked about dust and gas. Well, you see it's a blue tail coming up here and looking very, very straight. That is a gas tail, but it's an ionized tail. So things like ionized water, ionized carbon monoxide, or ionized carbon dioxide. And the reason I know that's an ion tail is it's going straight out from the sun. So the sun is down here, which you could probably guess from the picture there. So the sun is pushing back with the solar wind. It's pushing back against the ions and creating this long straight tail. This one here that's broader and whiter and curved is actually the dust, and it's following in the orbit behind the comet. So the comet has come in like this, and it's just following along. And that's what eventually just keeps streaming around behind it. And when our Earth's orbit crosses the orbit of a comet, you get a meteor stream. So I talked about there are 2 reservoirs, Oort cloud and Kuiper belt. Do all the comets have the same composition? When we first started looking at the spectrum of comets, they all look vaguely the same, but were they really the same? Well, that's what I started doing for my dissertation lots of years ago. And for 30 years, we used the McDonald 2.7 meter telescope, or 107 inch, to measure the composition of about 150 comets. I've looked at some really obscure comets. And we find there are 2 types of comets. There's what we call typical, and comets that seem to be missing the long chain carbon molecules. And by that, I mean things that have C2 in them, C3 in them, not all carbon, because CN is perfectly normal, but it's missing the long chains. So what do I mean by this? This is a spectrum. If for most of you, it may be just a squiggly line, but it tells me this goes through the whole optical part of the spectrum, the part that your eye could see, a little extreme on both ends. And we see these features that stick up. This is Comet Tuttle. And they're due to molecules. So NH, CN, C3, CN, CH, C2, C2, NH2. Any chemists in the room are going to go, wait a second, those aren't stable. Those are parts of things. Well, that's one of the problems with observing in the optical. All we see is the parts of things. When the ice comes off the nucleus in the sublimation, it may come off as something like acetylene, but very quickly the sun dissociates off those H's because they're not bound on very well. So pretty soon you have C2 left. Acetylene is C2H2. And that's perfectly stable, but C2 is not perfectly stable. So this is a typical comet spectrum. At almost precisely the same distances from the sun and the Earth, we looked at comet Giacomini-Zinner. And you don't have to be an expert on spectra to realize they don't look the same. They got the same strong feature, the CN. Yeah, that's there. And this one's CN, it's there. But maybe this one is that one. And we're missing a lot of things. So that's the depletion of the long chain carbon molecules. And so we can study this, and there have been three major groups who've been studying this. And you look at one species, C2 versus CN, C3 versus CN, and then this is NH versus CN. And you'll see there's a whole group of objects here on this line that all look approximately the same. And then there's all this bunch underneath who don't look the same. They're missing something. Same thing here, not here. So we're missing the long chain carbons. About 75% of the comets we observed are typical, and we're now between the different teams. We're now up to almost 250 comets. 25% of those are depleted of their long chain carbons. So does that mean they come from the two reservoirs? One's from one reservoir? No, nothing that easy. Some of the depleted comets are from the Oort cloud, and some are from the Kuiper belt. So there are typical comets in both reservoirs. 37% of the Kuiper belt comets are depleted, and 18% of the Oort cloud comets are depleted. And this has been confirmed by all three groups. Same comets. We always agree. Something's not easy to understand here. But it gets even worse because you always have to have one object that spoils a good story. So in 2019, my previous postdoc was observing at the 30-inch at McDonald with filters imaging comets, special filters, narrow band, so they isolate things. And he said, something's wrong here. The wrong filter's in the wrong place, and he re-zeroed everything, and it still came out wrong, and he couldn't figure out what was going on. He says, I'm terribly confused. And he was doing a comet that he wasn't even supposed to be doing because it was too faint. But he had nothing else up, so he did this comet. So he calls me and tells me, and I'm going out to the 107-inch 2 weeks later. I said, I'll take spectra of it. We'll see what it's doing. And it didn't look like any other comet we'd looked at. So we notified every comet people we couldn't think of. And we turned on virtually every telescope on the planet to look at this, to see what was going on. So on the left, you have an average comet. You can see, as I mentioned, that there's 80%. The blue is water. CO2 is green. CO is orange. And everything else is in this other wedge. Same color scheme. This is this comet, 2016 R2. CO is 80% or a little more. Water is 1 or maybe 2%. CO2 is pretty good. N2, we don't even mention N2 over there. N2 is really fairly strong, and then everything else. And we went, huh? What does that mean? And we've taken this stuff to meetings, and you get people go, oh, well, it's this, and this. And you go, yeah, but it doesn't have any water. And they go, oh, how do you explain it? We don't. We're looking for somebody to explain it. And there are now theories for how it can come about. Everyone has a little bit of flaw in it, but this guy, is either something. He's not an interstellar comet. We know this because his orbit is not compatible with an interstellar comet, but he's either formed in some very funny manner. Maybe he was a really large comet, and this is the and it differentiated, and this is the center. We don't know, but this is why we do science, because you get one of these that goes, huh? That's funny. And I've always thought that's Isaac Asimov got it right when he said, science is not looking in the microscope and going, eureka, I found it, but huh? That's funny. And that's what we've got, is that's funny right here. So we did all of the breaking it into different categories. And then, that gets after 150 comets, you don't have to keep doing that. And we know that comets formed in relatively cold conditions, probably 20 or 30 degrees Kelvin, not Fahrenheit. And when the ice are frozen forms of molecules, so that when they sublime, we get molecular gas. And molecular gas has these incredibly rich spectra. Each molecule has many lines in the spectrum. So you either look at them in very low resolution, which is what we did for all those years, for 30 years, trying to sort them into areas and just adding up the whole band, and that's what I've already shown, or you go to high spectral resolution. And McDonald has one of the best telescopes for doing that anywhere in the world, even without being a really big telescope. And we have excellent access to it. And so our program is the major contributor of high resolution comet data in the world. And what am I talking about? Well, going back to the Tuttle spectrum, where you see all these features, if you take this little narrow thing and look at it in high resolution, look at all these lines. And what we do when we're studying this is we look at the ratio of one line to another line. And then there are little things under here that we look at because they're telling us something. So we see this pattern change depending on conditions the comet is in right now. The C2 band, which is just huge and whopping, looks like this, and it's just got a zillion lines. And we can, again, look at the ratio of the different lines and learn about conditions when the gases were formed. So what do we learn at high spectral resolution? Instead of adding up all the flux and comparing one molecule to the other, now we can study the relative strengths of light. And one of the things we use it for is isotope ratios. So an isotope of two species are two species with the same number of protons, which is their atomic number, but different numbers of neutrons. So they have different mass, but very close. So C12, C13, which basically everything in the solar system looks the same. It's all about 89 or 90. Or 14 nitrogen versus 15 nitrogen. That is quite variable across the solar system and tells us different things. What that yields to us is information on the fractionation history of the gas. Now you're going, fractionation history, what does that mean? Fractionation is a process for separating out parts of a mixture. So if you get to a temperature where it's too warm for, it's too cold for something like CO to, or try this again. If you had CO and water mixed in, water stays in the ice form to much warmer temperatures. So as you come in and you heat the nucleus, before you get to where water gets heated enough to turn into the gas phase, you'll have CO go in the gas phase and disappear. So it separates out the CO from the water. It's a function of temperature, density, and pressure. So if we can study the spectra and we can learn about the fractionation, we learn about the temperature, density, and pressure when the solar system formed. It's a function of exchanging different parts. It's fairly complicated, but we can incorporate all this into our models of understanding the comets and the solar system. The only problem is we need to know when we look at this, where did that particular comet form? And so we only have the vaguest idea of, well, those all formed in the Jupiter-Saturn region, or those formed in the Kuiper Belt. But, the Kuiper Belt has a large distance range, and so we're not great on the details yet. But this is a plot showing D to H, which is hydrogen, and deuterium. Deuterium is the heavy form of hydrogen. SMO is standard mean ocean water. So this is the Earth right here. And you see Jupiter and Saturn down here, which is about the values of the protosolar nebula. And comets are up at this end. So they don't look like the protosolar nebula. So why am I giving you this picture? Well, because there are things that have changed it with comets. But one of the questions we have is, did the comets bring the water to the Earth? Well, these comets here have a value that's different than the Earth. So no, they can't be the same as the Earth. But these here look like the Earth. So maybe some of the water for the Earth was brought from comets. Probably not all. But there are other reasons to believe some of it has to have come from comets coming into the inner solar system. So one of the things I did in the last couple of years was watch a comet turn on. First of all, we had to, because of the pandemic, we had to remotely observe from Austin. We'd have somebody running the telescope in West Texas, and I'd sit in Austin in my house and observe, but it works pretty well. So we observed comet C2017 K2 pan-STARRS. It becomes a very big mouthful. And you have to say most of the mouthful because there's so many comet pan-STARRS that you got to differentiate. But we watched it going from Jupiter's distance, 5 AU, to about 2.5 AU, so a little bit past Mars. And we think that water cannot sublime until about 3 AU as it's coming in. So we said, what would it look like to look at the spectra at high resolution as the different features turned on? If everything was trapped within a cage of water, that's called a Clath rate, and some people think that's what it is, then you'd have to wait for the water to turn on before anything else would turn on. If they were separate little lumps of stuff, they could turn on independently. So it tells us about the structure of the ice. So this is the CN over that time. In all these plots, the bottom one is Comet de Vico as a comparison because it's a fabulous comet. And you see at 5 AU, we didn't detect anything. And then by 3.4 AU, well, there's some lines there. It's definitely detected, but they're not very strong. And you don't have any lines. You don't have any of these lines out here. This comet's at 0.7 AU, so it's inside the Earth's orbit. And it came on and got stronger and stronger. And if you're looking at it carefully, you'll notice that the ratio of the lines changes. So yes, definitely, this thing turned on. And so by 2.47 AU, when unfortunately it went too far south, we definitely had a full-fledged comet in CN. If we look at C3, well, we didn't have it at 5 AU. We didn't even have it at 3.4 AU, probably maybe at 3.24 AU and onward. This is, again, Comet de Vico and much better spectrum, a little brighter comet. Pan-STARRS was about 11th magnitude at its brightest. De Vico was about 5. And then C2, which I showed you that very complicated spectrum. And here's de Vico with all these lines in it in a very important pattern. And nope, nothing there, nothing there, maybe, probably, and then it's there. So we can come up with a chart that says we now know what species activated at which distance. And they didn't all activate at the same distance, and they didn't all activate just at 3 AU. So it must be a mixture of things intimately mixed together, but not caged together. So coming attraction. Recall earlier I said very little of the surface of the comet is active, and we see almost no ice on the surface. This is a deep impact spacecraft view of Comet 9P Tempel 1. It's a combination of the optical and some infrared data on top. And the infrared data is shown in the blue because that's ice. And this does not look like a dirty snowball. This looks like a big rock. And that's because it mostly is a big rock and with very, very little ice. So the coma comes not from the whole thing, but just from these little pieces here. And if we look at Tempel 1 again, this is a picture from Deep Impact. This is a picture from Stardust Next when it flew past Deep Impact, flew Tempel 1 several years later. You look at the same feature, which this is our flat guy, and you can see there's differences in it. So that's the ice subliming away. And this area here is different than this area here. So things show change, but there's still not a lot of ice on the surface. Well, we can estimate the amount of surface that's active or icy by figuring out if you took a ball the same size as the comet and it was total ice on the outside, and you had all sublimed, if it all sublimed, 100% of the surface is active, and otherwise, what fraction of the amount that what you could get are we seeing? And we find that for most comets, the active fraction is less than 25%. So these dirty snowballs, the ice is inside, it's not on the surface. But there is a handful of comets, and I mean a handful, 6 or 7. That's 2 handfuls, but that seems to be 100% active, and maybe even a little more than 100% active. And one of them is, I mentioned I'd come back to Hartley 2. This is Hartley 2, and he was thought to be slightly better than 100% active, which we couldn't explain, because how can you get better than 100% active? And when we take a picture, he doesn't look like he's icy over the whole surface. He's got this really nice smooth area here, and he's rotating around an axis there. So he's going in and out of the picture. One end looks much brighter than the other, and the other end has nothing coming off here. It comes off here. And once we get spectra of it, this is CO and this is water. They're not the same. So what we discovered as we took spectra of these things is some of this material is CO, but the rest is little chunks of ice. And so the more than 100% ice is ice crystals that have come off and then are sublimating. So that's why it looks like it's bigger than it is. So why am I telling you this story? Well, it's coming back. It has an orbit period of a little over 60 years, and every other orbit is totally unfavorable for viewing from the Earth. And 2023 is a favorable orbit. 2010 was when we flew past it. 2023 is a great orbit for it. And I put a finder chart here, and you can find finder charts for all the brighter comets up on this site. It's by Seiichi Yoshida, and you can see here's Gemini and Cancer, Origi, Perseus, and it's coming down, and it's with dates, and you can see it's going to stay in the northern hemisphere, thank God, and it's going to come where we can see it. So where is it relative to the sun and all? Perihelion, closest approach to the sun, is 2023, 12 October. The perihelion distance will be 1.05 AU, so just slightly past the orbit of the Earth from the sun. It will get to 0.4 AU from the Earth and be a total magnitude of about 7. Not naked eye, not Hale-Bopp, not even NEOWISE or anything like this, but really very exciting because we're going to team up and get as many telescopes as we can to obtain spectra in both the optical and the IR to try to understand how has it changed since we last looked at it 12, 13 years ago. And so this is what I do for a living. I chase comets. I don't find them, but I chase them and try to study them chemically. Thank you. And I will be happy to take pictures, to take questions.
I appreciate the talk. Thank you very much, Dr. Cochran. That was really interesting. I had a question with 103P Hartley 2. I know you said you were going to have a lot of telescopes trained on that. Is there an opportunity there for amateurs to help, or is the equipment needed a little too sophisticated?
No, astronomy is a funny field because we use amateurs all the time to help. Yes. So depending on what you have, whether it's just measuring the brightness or measuring or, being able to image it through a filter or, taking a picture of what it looks like at any particular time. Yes, these will all get coordinated in. It's one of these things. I don't know who's going to end up doing the coordinating. Probably the guys at University of Maryland, because they do that most times. But yes, we always appreciate amateurs looking at it.
I will follow up on that at some point and see if there's something we can do, and then get other club members involved in that and hopefully contribute to the research there. So appreciate that. I mean, go ahead. I'm sorry.
We're going to be trying to use what we'll certainly be using McDonald and its high resolution spectrograph and its 30-inch telescope, but we're hoping to use both of the Keck telescopes because they're a little larger.
Right. Just a tiny bit.
Yeah, but they're hard to get time on.
I understand. I think Pradeep had a question in the chat. Pradeep, do you want to come off of mute and ask your question?
I'll pop the chat also.
Oh, no, Mike. Okay, I think he said comment regarding if comet is source of water on Earth. A couple of days back, there was a story of the discovery of deuterium isotope in Orion's star system, which leads them to believe that the water on Earth may predate the solar system.
It's always interesting to try. I mean, Orion is a wonderful star-forming region. It's always interesting to try to figure out what will survive the formation of the solar system. Right. And water may be a little too delicate, but we see water all sorts of places in the universe. And if you have hydrogen, you have oxygen, you have water.
Right.
So we don't know yet. And the real test of it would be the isotope ratios, the D to H. And what values do you get from that? And the problem is it's the comets that aren't exactly cooperating because they're very, very hard to measure in a comet. And so we only have a handful of comets that have sort of measurements in them. If you put 5 comet people in the room, you'd have 6 opinions on whether there's an Earth signature of water.
Right. Okay.
We proposed a mission to NASA that would have ended the argument, but they didn't pick us.
No.
And it would have been to Hartley too.
Really?
Yeah.
That's unfortunate. The other question I had, and I'll let people come off of mute here and ask, sorry to kind of hoard all of the questions here. You mentioned C2016R2 and kind of the odd nature of it. Did you mention the word centaur? I thought I heard that because I remember that.
No, he's not a centaur.
Okay.
He's got a 20,000 year period, so it's not an interstellar comet.
Okay.
That we know, because you can't get into that orbit easily from an interstellar things, but it's much longer orbit than he's an Oort cloud comet. There's no question. Okay. Yeah, there's no question that he's an Oort cloud comet, but what he's trying to tell us, we don't know. And, okay, I've looked at 200 comets. Dave Sliker's looked at 250 comets. Most of those overlap with one another. So maybe between all of us, we've seen 400 or 500 comets. So that's one oddball. Well, there's got to be more of them. We just don't know how to find them. And this one was so much serendipity, but important serendipity, because, and it was one of the crowning moments for the comet community, because everybody cooperated with everybody else. There was nobody out to just make a name for themselves. They just all contributed, and we discussed by email. And it's like, well, I got this, but I don't get this. And it was great.
Wonderful. Okay. Does anybody want to come off of mute and ask any questions they have of Dr. Cochran here?
Yeah, Joe, this is Bill Spazeri. I have a question, and I'm sorry. First of all, thank you. Your presentation, not only did it have a lot of great information about comets, but it was actually reasonably easy to understand.
Well, thank you. I'm glad.
It's wonderful. Thank you very much. And just based on your experience and what you've done, it's very inspirational to me. And so I have to, pardon me if I'm getting a little personal here, but I'm curious about your education, how you got into astronomy, and why have you dove into comets the way you have, if you don't mind.
No, it's actually, it's an interesting story, sort of. I grew up in Long Island. There was no sky. I didn't, my dad had been a navigator in World War II, so he showed me what little you could see of the constellations, but he was actually a lawyer, but he liked the sky. And I was always interested in science. I had two older brothers who, one couldn't do science and the other one thought it was boring. And Grumman every year had a open house, which I found fascinating. My brothers both were bored to tears. But so I went off to college to be either a chemist or a physicist. And I had a advisor in college, which was Cornell University, who thought that everybody needed a well-rounded education. And he didn't mean English and all that stuff, because we had to take that anyway. He wanted me to take one of every science. The first one I managed to fit into my schedule was astronomy, and I was hooked. And that's literally how it happened. So I would have been a physicist. Well, I have my bachelor's is in physics. And so at that point, I decided that, I'm going to go to astronomy. And I had an advisor at Cornell another advisor in astronomy who wanted to make sure, I was going in the right direction. And so in those years, it wasn't very common to have women in the field. So he made sure every place I got into, I was being admitted because I was capable, not because I was a woman, which more power to him. And then I guess he was ruminating on what I could do, especially considering that I now had McDonald Observatory at my beck and call. And he said, it'd be really interesting to follow a comet in from aphelion, farthest distance from the sun, into perihelion. So that's what I set off to do. And the first comet we looked at was Encke, and Encke is the shortest period comet known. And what we didn't know at the time is it tends to go into outburst at 4 AU. People didn't believe us for a while until they saw it do it. But that's how we started off. But that's how I got into comets, basically. And so I got my master's doing stars at the University of Texas, and then switched to doing comets for my PhD.
So you got into comets and you were never seen again after that, huh?
That's about it.
Listen, like I said, your presentation was wonderful and you're a real inspiration. Thank you very much.
Indeed.
You're welcome. But don't put me on missions. I have very bad luck on that. Graph, as you mentioned, I was on, never flew. Contour blew up 6 weeks after we launched.
Oh no.
Yeah, and every other thing else I've proposed for, we've not gotten. So
Wow.
I'm not good at this.
The next one's going to be different then.
No, I've given up playing that
No,
game. You know,
okay.
you got to be young to be in a mission.
Got you.
When you launch and it's 6 or 7 years till something happens,
Right.
unless you blow up at 6 weeks. That was a bad day, really bad. We were
I can only imagine.
We were in an orbit around the Earth, in the geocentric orbit, and we were kicking out to an orbit around the sun, and we were 2 seconds from the end of the burn when we blew up.
Oh, goodness.
2 seconds.
Wow.
Yeah.
But you're still smiling.
It's been a lot of years. I've healed.
All right. I think we had a question from Don Selling. Don, do you want to?
Actually, I've got two. This last comet we had that was close.
ZTF.
Yeah, ZTF. It got in the press. It was the green comet.
The green comet. That's right.
Everybody asked me, "What about this green comet?" Okay.
Yeah.
The question I have: am I correct? Is it the CN that causes the green color?
No, it's a C2.
Oh, it's the C2. Okay.
Yeah. And that's the part that's in the green.
Pretty much all comets that come close enough are green, right?
Yep, pretty much. I could show you more pictures of green comets. The thing was, they went kind of crazy with this, and I'd been out at the observatory doing engineering type stuff, and our people out there said, "NBC wants to shadow you," and I'm like, my next observing run, I'm going to be in Austin, and besides, it doesn't come up until 4 a.m. They don't want to shadow me. They didn't. But it was, it was like, really, guys, this isn't that interesting. It hasn't been around in 56,000 years. Yeah, so what? This is, so it gets pretty funny at times, but every once in a while you have a really great comet, and then you want people to notice it.
Yeah, for sure. The other question I had, the spectra you were showing were all smaller chain carbon molecules. Do you ever get the opportunity to see if there are larger carbon molecules?
Not in the optical, because they don't have transitions there. But yes, in the infrared, we study longer things, and we try to match the infrared observations with the optical, so we can look and see how the things, as you move away from the brightest part of the image, which we call the optocenter, because you're not seeing the nucleus. Right. You want to look at how that compares with parent and daughter species or granddaughter species. So yes, that's how we have a good idea of what causes what.
Gotcha. Okay, and that because it seems to me that there's been a lot of discovery over the last 20 or 30 years of biological kind of molecules in both comets and asteroids, right? So,
well, if you look at some of the spacecraft data, Stardust brought back actually comet dust with it, and from VILD-2, and when they look at that in the lab, they see things like glycine, which is pretty long and is definitely a life type precursor, but whether there was, whether that's just coincidental, but yes, we see those kinds of things.
Okay, thanks. I appreciate it.
Okay. Dr. Cochran, could you entertain us with 2 more questions? Would that be too much of a lot? Okay.
No.
I believe Bill Pellerin, who you may be familiar with.
I do know Bill,
okay,
yes.
I was going to say he had a question, and Bill, I don't know if you want to come off of mute and ask your question, or if you want me to ask it on your behalf.
Let's see. Oh, I had to find the unmute button.
There it is.
That's the standard thing in Zoom. Where's the unmute button?
Exactly.
Yeah, right. So Anita, I was going to ask you, the GMT is coming on in 2030 or thereabouts. Right. And the question is, what can we do with that telescope that we can't do now?
Well, I am going to be retired by then, but the instrument that most intrigues me for looking at comets is GMT NIRS, which for those who aren't familiar with the GMT, it's Giant Magellan Telescope Near Infrared Spectrometer, and it's actually being built at the University of Texas by Dan Jaffe's group. It is very similar to an instrument that is running on the IRTF, the Infrared Telescope Facility on Mauna Kea, but it's a much bigger telescope, and B, it's a better version. And so it's very high spectral resolution over a really broad part of the infrared. And I think that's the one that's going to unlock a lot of things about what's going on, because it will be able to get a lot of the different parents as a function of different distances in the solar system. And so I think that's going to probably be, from my point of view, that's probably going to be the best thing that will come in comets. They probably won't like comets because they've got all this fancy AO stuff, and so they want something that can turn into something really sharp, and comets are this big, and so.
Is the IRTF the NASA observatory?
Yes.
Thank you.
Well, one of the NASA observatories. Yes. It's the infrared telescope. It's a 3-meter at Mauna Kea. And they just revised the high resolution spectrograph, putting in some of the special grading parts that Dan Jaffe built. And that's given them incredible capabilities. And one of the nice things about the IRTF is they don't care if you observe during the day, which works pretty well for comets.
Right. Okay. And the final question, Blanca Behar asked, Blanca, do you want to come off of mute and ask your question?
Yes, I was wondering about the Oumuamua. I don't know how to...
Maya. It's a Hawaiian. It's a Hawaiian name.
Is that a comet or is it an asteroid?
Well, we don't know really. There's a lot of controversy, and there'll be a lot of people will say it's definitely this, it's definitely that. It is an interstellar object. It did not form around our sun. It formed around some other planet, and it got loose, and it managed to cross into our solar system. The definitional difference between a comet and an asteroid is, does it have a coma? Does it have that surroundings material? It does not. But there are people who think that they've measured that it's either speeding up or slowing down. I don't remember which sense they have it in. And that has to be because it's pushing out jets of material. That would be indicative of a comet, because really we have things that look like comets in the asteroid belt. So it's neither because it's not one of ours, but it may have water ice or hydrogen ice or something. And it's still very contentious what exactly it is. And I actually haven't looked at it in Maya, but Borisov is the other interstellar object, and that one looks very much like a comet. It has a coma. Its spectral look the same as our comets. So that may be telling us that what the leftovers in our solar system are maybe very similar to what's leftovers in other planetary systems that are formed. And now we know there's at least 5,000 planetary systems in the universe, or in the Milky Way.
And growing, right?
And growing.
Absolutely.
Yep.
Well, Dr. Cochran, thank you so much for the presentation tonight. As others have said, this was absolutely wonderful. We appreciate your time and sharing much of the work that you're doing with us in a way that many of us can comprehend and understand. So hopefully when we make it out to West Texas next month, if you're out there, when we take the tour of the McDonald Observatory, we have an opportunity to meet you in person. And if not, we hope that we can help contribute to some of the citizen science opportunities that we have with 103.
Yeah, and you talked about dark skies. Are you aware that that part of the state is now part of the world's largest dark skies reserve?
Absolutely.
First anniversary, and it goes into Mexico, and it's unbelievable.
Absolutely.
And we're actually thinking maybe it's slightly darker than it was a year ago, but maybe not.
Really? Is that
that'd be
dissipation of the Hunga Tonga ash cloud that kind of enveloped the entire Earth that we think that might have contributed to some of the brightness, the reflection of the light off the upper atmosphere? Or
mostly it's the oil industry, and you've got to get them to understand that you don't want to have your lights going everywhere. You want them to go down.
Right.
And they're trying to get there now. So it's catching on, and we now have a program where we reward businesses that do proper lighting and things like that. It's very, very impressive how dark it is at McDonald compared to, say, Kitt Peak, or certainly places like Lick and Palomar.
Indeed. Well, we're looking forward to enjoying those dark skies next month. So hopefully we'll have an opportunity to, maybe see you there if the timing works out. So
yeah,
thank
I'm
you
not
again.
sure if I'm going or not.
Yeah.
All right.
Okay. Thank you again. And everybody, thank you for joining us tonight. I hope you enjoyed the presentation as much as I did, and it looks like others did as well. Our next meetings will be May 4th for our novice meeting next month, and May 5th for the general meeting. Again, those will be online. Hopefully I'll have some news to share about potential in-person meetings again. So stay tuned for that. And if you're on social media, there are links to our social media platforms. You can catch the recording of this presentation on YouTube. And as I always say, if you have any questions for us, please send us an email, info@astronomyhouston.org. More than happy to address any of those questions or concerns that you have. So Dr. Cochran, again, thank you very much. And to everybody who joined us, thank you. Stay safe, and we'll see you next month. Take care.
Thank you, Joe.
Have a great night.